Let's say we need to compute the mixed second-order partial derivative, f sub xy, where f is x times ln of xy. Remember, in shorthand notation, or what others call subscript notation for partial derivatives, the order of differentiation goes from left to right in the subscript. That means we should take the partial of f with respect to x, and then take the partial of that result with respect to y. However, the more efficient way to go about this problem is to take the partial of f with respect to y first. So we are going to compute f sub yx instead in just a moment, even though that object is not of our interest in the first place. Now, you ask, wouldn't we get a different partial derivative? Well, not really, because of the Clairaut's theorem. Please excuse my poor French pronunciation, dear French speakers. The Clairaut's theorem is more commonly referred to as the equality of mixed partials theorem. Putting aside the technical sufficient condition for it, it basically guarantees that mixed higher-order partials can be computed in any order of differentiation for most, if not all, of the functions that engineers are faced in real applications. You just need to be careful about the points of discontinuity for the mixed partials. The focus of this hands-on video is not those technical details. So let's get started and see how we can benefit from the change of differentiation order. Now, to differentiate f with respect to y, we treat x like a constant, and so we are actually differentiating something like a single function of y in the form of a times ln of by, where a and b are constants. This is going to be pretty straightforward. We factor out x, and we are left with differentiating just the ln of xy with respect to y. To compute that, we apply chain rule. Derivative of ln something is 1 over that thing. So we have 1 over xy times the partial of that thing xy with respect to y, which is simply x. Collecting everything together, we have x times 1 over xy times x. One copy of x on top cancels the one at the bottom, and so we have x over y. This is f sub y. Now, let's differentiate f sub y with respect to x to get the mixed partial we are after. So we have the derivative of x over y with respect to x. That's even easier. By holding y constant, this is like 1 over y times an ordinary derivative of x with respect to x, which is 1. Finally, we have 1 over y, and that is f sub yx, which is the same as f sub xy by the Clairaut's theorem. So, with just a few steps, along with only one application of chain rule, we got the result. I told you up front that this is going to be more efficient than computing partial f partial x first. The key is indeed the fact that we started with a function that can be treated like a single variable function when we took the first partial. Bear this in mind for now. Now, let's see what it takes to differentiate f with respect to x first as instructed. Here, we immediately see what makes this route relatively inefficient. We are dealing with a product of two functions of x when we take partial of f with respect to x. Then, we apply product rule, which gives us two terms, two derivatives to handle. The first derivative is dx dx, which is 1. The second one is a partial that is similar to what we've handled when computing partial f partial y using chain rule. This time, we have a partial with respect to x instead. The partial of x times y with respect to x is y. After simplifying things, the second term is just 1. So altogether, f sub x is ln of xy plus 1. Although this is not super complicated comparing with f sub y, and as you can foresee that the extra constant one is not going to cause any trouble when we next take partial with respect to y, we did spend some extra steps to get to the result for the first partial of f. Now to complete the picture, now we differentiate f sub x with respect to y. To do so, we apply the sum or difference rule. And again, we end up with two derivatives, although they are relatively simple and familiar. The first derivative is exactly what we computed when we did f sub y, so the first term is 1 over xy times x, which is 1 over y. The second term is a derivative of a constant, which is of course 0. Putting everything together, f sub xy is 1 over y. Same result as before, but we used chain rule twice, and we also needed to apply product rule and sum rule. Well, in exchange we have also verified the Clairaut's theorem, that is f sub yx is identical to f sub xy. But what's more important is to be able to see why this route indeed takes a few more steps to get to the same mixed partial. This is because the function f is effectively more complicated in computing partial f partial x than in computing partial f partial y. Although the difference is not that huge in this case, the key takeaway is that when computing mixed partials, you should bear in mind you might have the freedom to change the order of differentiation, and so you should carefully inspect the multivariable function involved, and then pick the route that makes the calculation shorter and easier. Alright, I hope you enjoy this video, and I will see you in the next one.